Yeah, good morning, students. So the last class we discussed about Boyle's law, Charles' law, Galileo's and Avogadro law, and also we discussed about ideal gas equations and ideal constant and value of R. Correct, no? And also we discussed about gas constant R for a single molecule is called as Boltzmann's constant. Okay, but I forgotten to tell one definition for ideal gas. Okay, sorry for that. Ideal gas equation for that definition, sorry, I forgotten to tell. Ideal gas equation definition. You see, ideal gas we already see in the previous class. It obeys, means it follows. Okay, any gas which obeys or which follows Boyle's law, Charles' law and Avogadro's law simultaneously, then that gas is known as simultaneously, then that gas known as ideal gas. Ideal gas is nothing but which obeys or which follows the Boyle's law, Charles' law, Avogadro's in simultaneously, then that gas is called as ideal gas. Okay, next we are going to talk about the very important topics like Dalton law of partial pressures. Okay, before going to Dalton law of partial pressures, we are going to discuss a topic that is calculating the mass. Calculation of mass, molecular weight and density of the gas by using or by taking ideal gas equation. You see, calculation of mass. Okay, by using molar weight or density of the gas by using ideal gas equation. We know that the ideal gas equation is PV is equals to nRT. Correct? No, nRT. N already I told that it is n is nothing but same molecules. Correct? No, same molecules. N we will take that n small n is equals to mass of the gas by molecular weight of the gas. Mass of the gas will represent as small m and molecular weight will represent as capital M. You see, the n you will take that already I told while explaining the ideal gas equation. N is nothing but same number of molecules and also we talk that n is nothing but molecules having same. In Avogadro law we explained same number of molecules means mass by molar weight. You see, we are substituting small m by capital M. We are substituting in the equation number 2. PV is equals to, while replacing by n by small m by capital M RT. RT. Okay, we have the formula correct now. Then we will rearranging. Okay, if we rearrange, we will take that V by small m equals RT by P capital M. Capital M. You see, we are getting V by M equals RT by PM. If we rearrange this equation number 3, if we rearrange the equation number 3, we will get M by V equals P by capital M by RT. We know mass by volume is nothing but density. Density is nothing but now P capital M by RT. You see, at constant temperature, if the temperature is constant, then molecular weight will be also constant. Quite commonly, the ideal equation, ideal constant will be also the constant, it will be a constant. Then we will write that this term will be the constant. Okay, constant. We will take that at constant temperature R and capital M also will be the constant. Then D equals Kp, or D is directly proportional to P. Density is directly proportional to the pressure, while this expression will tell that density is directly proportional to pressure. Is pressure. Okay, you see, once again I will tell that the calculating of the mass and molar weight and density of the gas by taking ideal gas equations. The ideal gas equations, we get that PV is equals to nRT. N is that was same number of molecules. We take that mass of the gas, each gas, okay, and molecular weight of the gas. Okay, mass and molecular weight, we taken that small m and capital M. If you substitute in the above equation, you get PV is equals to small m by capital M RT. We know if you rearrange, V by small m equals RT. You see, it's coming below. Okay, Vm is equals to RT by Pm. Vm, if we rearrange this, we get M by V. M is nothing but mass volume. Mass by volume is nothing but density. Okay, I will write D is equals to mass by volume. Okay, while this we get density is directly proportional to the pressure. Okay, next we are going to talk about very important topic, that is Dalton's law of partial pressure. You see, we are going to talk about Dalton's law of partial pressure. You see, it was introduced by John Dalton in the year 1898. Okay, what he kept, you see, we already know that PVT, correct? No, PVT. What is taken? He kept the V and T as a constant. Okay, he kept constant. He taken the two gases. For example, I will take we kept temperature and volume kept constant. The same number of molecules will differ. We were taking here oxygen, here nitrogen. Oxygen and nitrogen. You see, this is N1, N2. You see, if we keeping this constant, but you see the temperature and volume will be constant, but number of molecules changing. If the pressure is applied on the N oxygen molecules, it shows, means at constant temperature, the total pressure X means total shows excreted, means excreted is nothing but applying the pressure by non-reacting gases. Means you see this react, no, it is first of all John Dalton was taken that, you see John Dalton was taken that is applicability. First of all you see it only is applicable for the mixture of non, you see this is word very important, non reacting gases. You see he is taken that non-reacting gases, it does not joined, and we are taking example non-reacting gases. You see what happens if it both pressures applied similarly, that N1 is oxygen, N2 is nitrogen. Here also temperature pressure is same. See here why is used to take non-reacting gases, because non-polar, I think you know that what is non-polar, already explained is non-polar molecules, okay. At constant temperature, total pressure excreted by the non-reacting agents is equal to the sum of partial pressures of individual gases. Means it's individual gases, means N1 individual gas, N2 individual gas is equal to, okay, partial pressure, the sum of the partial pressures is equal to total pressure of excreted by the non-reacting agent. You see he was telling that non-reacting gases, sorry, it's not a reagent, it is gases, it's not reacting, correct? No, then what happens if we apply a partial pressure to the oxygen and nitrogen, okay? See we are applying the pressure to the oxygen, we are applying pressure to the nitrogen. What happens, the total, here we are talking the total pressure excreted means applied, okay, for non-reacting gases is equal to, you understanding, the total pressure excreted by non-reacting gases is equal to sum of partial pressure of individual gases. See I am telling that, I will write the definition by seeing the diagram. Definition: at constant temperature, total I am talking total pressure excreted means applied by this is word very important, non-reacting gases is equal to sum of individual sum of the partial pressure of individual gases. If you write the mathematical form for seeing this diagram, you see we will talk that total pressure excreted, we take pressure total, correct? Now total pressure equals total pressure excreted by non-reacting gases is equal to sum of partial pressure. If you take partial pressure, this is P1, this is P2, correct? No, P1 plus P2. If you take 2 more 3 more gases, P3, P3, so on, we take Pi. I am not taking N because you will be again confused. Okay, for that Pi, this is equation number 1. See, this is equation number 1. We will tell that P1, P2, P3, it tells that partial pressure of gases. If you talk P1, partial pressure of gas P1 means particularly one gas P1. If you talk partial pressure of P2 means another gas. Okay, different gases. Okay, it tells the Dalton law of partial pressure is nothing but at constant temperature, the total pressure exerted by non-reacting gases is equal to sum of partial pressure of individual gases. Okay, next we are going to talk about applications. Applications of Dalton's law of partial pressure. You see, this is very important. While now if you understand the Dalton law of partial pressures, it will be easily understood. Okay, first in this first application, that is pressure of dry gas collected over water. So we not understand. Don't be any discourage. You will be understand easily now. The pressure of dry gases. What is this dry gas? Okay, collected over water. Okay, we will tell that. You see, this is we take a beaker. It is water is filled. Correct? No. If we dip a test tube, water will be flow. Correct? No. You see, when ಒಂದು ಬೀಕರ್ ಇದೆ, ಬೀಕರ್ಲಿ ಏನು ಮಾಡಿದ್ದೀರಿ, ವಾಟರ್ ಹಾಕಿದ ತಕ್ಷಣ ಅದಕ್ಕೆ ಒಂದು ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ ಇಟ್ಟಿದ ತಕ್ಷಣ ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ ಒಳಗಡೆ ವಾಟರ್ ಹೋಗುತ್ತೆ. ಅದು ಯಾಕೆ ಹೋಗುತ್ತೆ? ಬಿಕಾಸ್ ಆಫ್ ಸರ್ಫೇಸ್ ಟೆನ್ಷನ್. ನಿಮಗೆ ಅದು ನಾನು ಸೆಕೆಂಡ್ PUC ಚಾಪ್ಟರ್ ಇದೆ ಸರ್ಫೇಸ್ ಟೆನ್ಷನ್, ಅವಾಗ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತೀನಿ. ಇಲ್ಲಿ ನೋಡಿ, ಇವಾಗ ಏನು ಮಾಡ್ತಾಯಿದ್ದೀನಿ, ಈ ಬೀಕರ್ಲಿ ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ ಡಿಪ್ ಮಾಡಿದ್ದೀನಿ, ವಾಟರ್ ಮೇಲಕ್ಕೆ ಹೋಗಿದೆ. ಇದು ನಾನಿಲ್ಲಿ ಅಪ್ಲೈ ಮಾಡ್ತಾ ಇರೋದು ಏನು ಗೊತ್ತಾ? ಪ್ರೆಷರ್ ಅಪ್ಲೈ ಮಾಡ್ತಾಯಿದ್ದೀನಿ. ಈ ಪ್ರೆಷರ್ ಯಾವುದು ಗೊತ್ತಾ? ಅಟ್ಮಾಸ್ಫಿಯರ್ ಪ್ರೆಷರ್. ಅರ್ಥ ಆಗ್ತಾಯಿದೆ? ಅದು ಅಟ್ಮಾಸ್ಫಿಯರ್ ಪ್ರೆಷರ್. ಓಕೆ, ನೆಕ್ಸ್ಟ್ ಇನ್ನೇನು ಹೇಳ್ತಾ ಇದ್ದೀನಿ, ಇವಾಗ ಈ ವಾಟರ್ ಹೋಗಿದೆಯಲ್ಲ, ಈ ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ಲಿ ಇಲ್ಲಿ ಗ್ಯಾಪ್ ಇರುತ್ತೆ ನೋಡಿ, ಹೇರ್. ಈ ಹೇರನ್ನು ಹೇಳ್ತೀರಿ, ಇಲ್ಲಿರೋ ಹೇರು ಇಟ್ ಈಸ್ ಡ್ರೈ ಗ್ಯಾಸ್. ಅರ್ಥ, ಗ್ಯಾಸ್ ಮೇಲೆ ಇಲ್ಲಿ ನೀರು ಹೋಗ್ತಾ ಇದ್ದಷ್ಟು ಡಿಪ್ ಆಗಿದೆ, ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ ಮೇಲೆ ಹೋಗ್ತಾ ಇರಬೇಕಾದ್ರೆ ಇಲ್ಲಿ ಗ್ಯಾಪ್ ಇರುತ್ತಲ್ಲ, ಅದನ್ನು ಡ್ರೈ ಗ್ಯಾಸ್ ಅಂತೀವಿ. ಅರ್ಥ ಆಗ್ತದ? ಈ ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ ಹತ್ರ ಇಲ್ಲಿ ಮಾಯ್ಶ್ಚರ್ ಥರ ಇರುತ್ತೆ. ಈ ಮಾಯ್ಶ್ಚರ್ ಹೆಂಗಿರುತ್ತೆ ಅಂದರೆ, ಫ್ರಿಜ್ಜಿಂದ ನೀವು ವಾಟರ್ ಬಾಟ್ಲನ್ನು ತೆಗೆದ್ರೆ ಔಟ್ಸೈಡ್ ನಮಗೆ ಮಾಯ್ಶ್ಚರ್ ಇರುತ್ತಲ್ಲ, ಹಂಗಿರುತ್ತೆ. ಅದನ್ನು ನಾವೇಂತೀವಿ, ಇದನ್ನು ಇಲ್ಲಿರೋದನ್ನು ಮಾಯ್ಶ್ಚರ್ ಮೀನ್ಸ್ ಪ್ರೆಷರ್ ಆಫ್ ಮಾಯ್ಶ್ಚರ್ ಏರ್. ಅರ್ಥ ಆಗ್ತದ? ಮಾಯ್ಶ್ಚರ್ ಏರ್. ಮತ್ತು ನಾವು ಏನು ಮಾಡ್ತೀವಿ, ಇದಕ್ಕೆ ಒಂದು ಅಂದರೆ ಅಲ್ಲಿ ಈ ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ ಒಳಗಡೆಯಿಂದ ನಾವು ಏನಾದರೂ ಒಂದು ಪೈಪ್ ಕಲೆಕ್ಷನ್ ಕೊಟ್ಟು ಆ ಪೈಪ್ಗೆ ಹೇರ್ ಪಾಸ್ ಮಾಡ್ತಾಯಿದ್ರೆ ಅರ್ಥ ಆಗ್ತದ ಏನಾಗುತ್ತೆ ಅಂದ್ಬಿಟ್ಟು, ಅಂದರೆ ನಾವು ಕಲೆಕ್ಟ್ ಮಾಡ್ತೀವಿ, ಪ್ರೆಷರ್ ಕಲೆಕ್ಟ್ ಮಾಡ್ತೀವಿ. ಅರ್ಥ ಆಗ್ತದ? ವೆನ್ ಗ್ಯಾಸ್ ಈಸ್ ಕಲೆಕ್ಟೆಡ್ over water, it becomes moisture due to water vapors. ಈ ವೇಪರ್ಸಿಂದ ಏನಾಗಿರುತ್ತೆ, ಈ ಏರ್ ಹೋಗ್ತಿರುತ್ತಲ್ಲ, ಈ ಏರಿಂದ ಇದನ್ನು ಕೂಲ್ ಆಗಿರುತ್ತೆ, ಅದನ್ನು ಮಾಯಿಶ್ಚರ್ ಏರ್ ಅಂತೀವಿ. ಅರ್ಥ ಆಯ್ತಾ? ವಿಚ್ ಎಕ್ಸ್ಕ್ರೀಟ್ ಇಟ್ಸ್ ಓನ್ ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಅಟ್ ಸೇಮ್ ಟೆಂಪ್ರೇಚರ್ಸ್ ಆ್ಯಂಡ್ ಗ್ಯಾಸ್. ನೋಡಿ ಇಲ್ಲಿ ನಾವು ಏನೂ ಅಪ್ಲೈ ಮಾಡ್ತಾ ಇಲ್ಲ, ಅರ್ಥ ಆಗ್ತದ? ಮೈನ್ ಇಂಪಾರ್ಟೆಂಟ್ ಇದರಲ್ಲಿ ಏನಂದರೆ, ಫಸ್ಟ್ ನಾವೇನು ತಗೊಳ್ತಾ ಇದ್ದೀರಿ, ಫಸ್ಟ್ ಇದರಲ್ಲಿ ಅಟ್ಮಾಸ್ಫಿಯರ್ ಅಪ್ಲೈ ಮಾಡ್ತೀವಿ, ಅಂದರೆ ಪ್ರೆಷರ್ ಆಫ್ ಅಟ್ಮಾಸ್ಫಿಯರ್. ಕರೆಕ್ಟಾ? ಪ್ರೆಷರ್ ಆಫ್ ಅಟ್ಮಾಸ್ಫಿಯರ್. ನೆಕ್ಸ್ಟ್ ಏನು ಮಾಡ್ತಾ ಇದ್ದೀರಿ, ನಮಗೆ ಪ್ರೆಷರ್ ಆಫ್ ಡ್ರೈ ಗ್ಯಾಸ್. ಕರೆಕ್ಟ್ ಅಲ್ಲ? ಪ್ರೆಷರ್ ಆಫ್ ಡ್ರೈ ಗ್ಯಾಸ್. ನೆಕ್ಸ್ಟ್ ಇದಾಗಿದ ತಕ್ಷಣ ಏನು ಬಂತು ನಮಗೆ, ಪ್ರೆಷರ್ ಆಫ್ ಮಾಯಿಶ್ಚರ್. ಏರ್ ಪಾಸ್ ಆಗಿದ ತಕ್ಷಣ ಈ ಏರಿಂದ ಇದು ಕೂಲ್ ಆಗಿ ವಾಟ್ರಿಂದ ಅಟ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಟೆಂಪ್ರೇಚರ್ಸ್. ಓಕೆ, ಮಾಯಿಶ್ಚರ್ ಬಂತು. ಓಕೆ, ಇದು ನಮ್ಗೆ ಫಾರ್ಮುಲಾ ಬಂತು ಬೈ ಸೀಯಿಂಗ್ ದಿಸ್ ಡಯಾಗ್ರಾಮ್. ಓಕೆ, ನಾವಿಲ್ಲಿ ಇಂಪಾರ್ಟೆಂಟ್ ಏನು ಬರೀಬೇಕು, ವೆನ್ ಗ್ಯಾಸ್ ಈಸ್ ಕಲೆಕ್ಟೆಡ್ ಓವರ್ water, it becomes moisture due to water vapors when exit its own partial pressure at same temperature of a gas. Okay, ಇನ್ನೊಂದು ಇದು very very important, the partial pressure of water ಅಂದರೆ ವಾಟರ್ದು ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಆಫ್ ವಾಟರ್ ವೇಪರ್ಸ್ ಹೋಗ್ತಾ ಇರುತ್ತಲ್ಲ, ಟೆಂಪ್ರೇಚರ್ಸ್ ಇದಾದಷ್ಟು ವೇಪರ್ಸು ಹೋಗ್ತಾ ಇರುತ್ತೆ. ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಆಫ್ ವಾಟರ್ ವೇಪರ್ಸ್ ಈಸ್ ಕಾಲ್ಡ್ aqueous tension. ಇದು ಅರ್ಥ ಆಗ್ತದ? ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಹೇಳ್ತಾ ಇದ್ರಿ, ಆಕ್ವಿಯಸ್ ಟೆನ್ಷನ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಅಂದರೆ ಇದು ಪಾರ್ಷಿಯಲ್ ವಾಟರ್ ವೇಪರ್ಸ್, ಈ ವಾಟರ್ ವೇಪರ್ಸ್ ಎಲ್ಲಿ ಹೋಗ್ತದೆ, ಈ ಮಾಯ್ಶ್ಚರ್ಗೆ ಹೋಗಿ ಕುತ್ಕೊಳ್ತಾ ಇದೆ. ಕರೆಕ್ಟಾ? ಆವಾಗ ಏನು ಅನ್ಬೋದು ನಾವು, ಆಕ್ವಿಯಸ್ ಟೆನ್ಷನ್ ಈಸ್ ನಥಿಂಗ್ ಬಟ್ ಪ್ರೆಷರ್ ಆಫ್ ಮಾಯ್ಶ್ಚರ್ ಏರ್ ಅನ್ಬೋದಲ್ಲ. ಮಾಯ್ಶ್ಚರ್ ಏನು ಯಾವಾಗ ಆಗ್ತಾಯಿದೆ, ಈ ಟೆಸ್ಟ್ ಟ್ಯೂಬ್ ಮೇಲೆ ಮಾಯ್ಶ್ಚರ್ ಕುತ್ಕೊಳ್ತಾ ಇದೆ, ಅದನ್ನು ಏನಂತ ಇದ್ದೀರಿ ನಾವು ಆಕ್ವಿಯಸ್ ಟೆನ್ಷನ್, ಅಂದರೆ ವಾಟರ್ ವೇಪರ್ಸ್ ಕುತ್ಕೊಳ್ಳೋದನ್ನ ಆಕ್ವಿಯಸ್ ಟೆನ್ಷನ್ ಅಂತ ಇದ್ದೀವಿ. ಆವಾಗ ಆಕ್ವಿಯಸ್ ಟೆನ್ಷನ್ we can also called what aqueous tension equals pressure of moisture air. ಕರಿಬೋದಲ್ಲ, pressure of moisture air. Okay, we got this correct now. If you, this is equation number 1, equation number 2. If you apply equation number 2 in equation number 1, in equation number 2 in equation number 1, okay, what happens, you see, P partial pressure of atmosphere equals pressure of dry gas plus I am replacing moisture air pressure equals aqueous tension. Now I am replacing aqueous tension. Correct? No. Main concept to find pressure of dry gas. The pressure of dry gas equals pressure of atmosphere minus aqueous tension. You see, we got the formula to find pressure of dry gas equals pressure of atmosphere minus aqueous tension. Very very important is aqueous tension is directly proportional to the temperatures. You see, aqueous tension is I can write 80, aqueous tension 80 directly proportional to the temperatures. If temperature increases, aqueous tension increases. Aqueous tension increases, the pressure of dry gases also increases, and atmosphere pressure also increases. Okay, next. Okay, I want to explain once again. You see, this is Dalton law of partial pressures. We are taking two gases, we are passing a pressure to that. but one gas will apply in the molecules its own, its non-reacting agents. Okay, if reacts means it become a pressure, but it is non-reacting gases. For that it became partial pressure of a oxygen, of a nitrogen. Okay, you see what Dalton law of partial pressures: at constant temperature and volume, the total pressure of excreted by non-reacting gases is equal to sum of the partial pressure of individual gases. See, individual gases are written same expression, and P1 P2 is the partial pressure of the gases. And applications, in applications, first it used to calculate the pressure of dry gases, or pressure of dry gases collected over the water, or calculating the pressure of dry gases. Okay, pressure of dry gases, we take a beaker, we fill the water. Okay, we keep on test tube, we are dipped in a test tube in a beaker. What happens? Water is entered to the test tubes, correct? No, if we atmosphere, this is the atmosphere pressure, then the gap is there in the test tube. That gas is the nothing but dry gas of a pressure. Then if the quite common, if you keep it in some time, what happens? The water is having temperatures, normal temperatures. In water, the vapors will be deposited in the test tubes. That is moisture air, the pressure, moisture air pressure. If you passing, correct? No, that is okay. We'll talk first. We'll take on that atmosphere pressure equals, and for atmosphere pressure we got dry gas, correct? No, then after dry gas what happens? Sometimes it became moistures. For that be moistures. This is equation number 1. The partial pressure of water vapors is partial pressure of, you see, partial pressure means water vapors of is nothing but partial pressure of water vapors is called aqueous tension. The aqueous tension is nothing but pressure of moisture air. If we substituted in the equations, we will get that pressure of atmosphere equals pressure of dry gas plus aqueous tension. We want to calculate the pressure of dry gas equals pressure of atmosphere minus aqueous tension. Next we are going to talk about another application, that is calculate second application, calculate the partial pressure, calculate the partial pressure, calculate the partial pressure. From the ideal gas equation we know that PV is equals to nRT. PV is equals to nRT. If you want to find out the pressure, P equals nRT by V, correct? No, we have the formula. Then if you apply the for two gases will R and T and volume will be same. Pressure and same number of molecules will be changing, like P1 equals N1 RT by V. Volume not changing, volume is constant. In this, volume and temperature and R will be constant. Okay, then for the one gas, if we take about two gases, P2 is equals to N2 RT by V. If we apply the equation, you see this is equation number 1, equation number 2, equation number 3. If we according to Dalton partial, according to Dalton's partial pressure, P total partial pressure, total pressure equals partial pressure of 1, partial pressure of 2, partial pressure of 3, so on. We'll take Pi. Okay, if you substitute, this is equation number 4. You see equation number 2 and 3 in equation number 4. Equation number 2, 3 in equation number 4. Equation number 2, 3, in equation number 4. P total means total pressure equals P1 is equals to N1 RT, correct? No, by V. P2 equals N2 RT by V. For example, we take P3 N3 RT by V. So on, you can write Ni RT by V. This is equation number 5. Okay, you see, while seeing these equations, we can make a common no. P total pressure equals N1 plus N2 plus N3 plus so on Ni RT by V. Equation number 6. See, in this equation number 6 will tell that the total pressure of a gas excreted and applied by the system is depend correct? No, it depends upon the amount of the gas present in the system. Means same number of molecules will tell that amount. Okay, amount of gas present in the system depends upon the same number of molecules. Okay, next you see, while apply this, you see equation number 6 and equation number 1, equation number 2. Okay, equation number 2 is P1 equals N1 RT by V. The sixth equation is P means total pressure will gives this same number of molecules into ideal gas temperature and volume. Okay, this is equation number, already I written that equation number 2, correct? No, again I am writing P total equals N1 plus N2 plus N3 so on Ni by RT by V. This is equation number 6, already I written that. Okay, if you subtract equation number 2 by equation number 6, P1 divided by P total means total of pressure equals N1 by RT by N1 plus N2 plus N3 so on Ni RT by V. RT by V. You see here what happens, RT by V and RT by V is cancelled. We will get the expression N1 plus N2 plus N3 so on Ni. You see the P1 by P total. You see what is this? This equations will tell moles of first gas. This is moles of first gas, correct? No, this is total moles of system. We will write that. We can write moles of the first gas equals, this is total amount of the system. Okay, we will write that this is equals to x1 is mole fraction of a gas. We will also write that mole fraction is equals to mole of the first gas divided by total mole of the system. Mole fraction of a gas, P1 by P total. We can write P1 because we want to find out partial pressure of the first gas, correct? No, partial pressure of the first gas equals to mole fraction of the gas into total pressure, okay, total pressure. See, this is two applications are very important. Again, I'll explain this. You see, calculating the partial pressure, we got the PV is equals to nRT by the ideal equations. We can take that pressure is equals to nRT by V. If you apply for the first gas, second gas, we get this expression. According to the Dalton partial pressure, total pressure equals to partial pressure, sum of the partial pressures, correct? No, we will return the expression. The equation number 2 and equation 3 is substituted in the equation number 4. We get total pressure is equals to N1 RT by V, N2 RT by V, N3 RT by so on. Then if you take N1, N2 means if you take RT by V means constant terms at the right side, we get P total pressure equals N1, N2, N3 so on RT by V. Equation number 6 means this equation will tell that total pressure is excreted by the system is depends upon the amount of gas present in the system or same number of molecules, okay, based on the N, okay. Then P1 is equals to N1 by RT by V. We already get the pressure of the first gas, partial means pressure of the first gas is we taken and divided by the total pressure, we get equation number 2, equation number 6. If we substitute the RT by V is cancelled, then N1 plus N2, N3 so on. N1 is nothing but mole. This is mole of the first gas. This is total mole of the system is equal to mole fraction. Okay, mole fraction is denoted as x1. Then P1 by means pressure of the first gas divided by total pressure equals to mole fraction. We want to find out the pressure of means partial pressure of the first gas. Partial pressure of first gas equals to mole fraction into pressure of the total gas.